A groundbreaking peer-reviewed paper has just reclassified the interstellar object 3I/Atlas. Its conclusions fundamentally challenge everything NASA has told the public since the object's discovery in July 2025. The visitor hurtling through our solar system at 290,000 kilometers per hour is behaving like any comet we've ever studied. Emerging evidence suggests it might be something far more remarkable, a crystalline remnant from a planetary system that perished billions of years ago. The research team examined 15 independent observational studies, constructed sophisticated thermophysical models, and tested survival scenarios across interstellar distances. Their findings are remarkably direct and unusually definitive for scientific literature. The paper explicitly states that 3I/Atlas is inconsistent with cometary nuclei, and the accumulated data points toward two alternative explanations, both requiring geological processing on a planetary scale. The first possibility involves a fragment from a differentiated exomoon. The second suggests lithified planetary crust, material that was compressed and crystallized over millions of years under conditions similar to Earth's sedimentary rock formations. If this new classification proves accurate, we're not merely observing a simple visitor from the depths of space. We're witnessing a piece of planetary architecture from another world, a fragment that survived the catastrophic destruction of its parent body and traversed light years through radiation, micrometeorite impacts, and extreme thermal conditions without disintegrating. This isn't speculation built on incomplete data or ambiguous institutional responses. This is published research that directly contradicts the official narrative, and it raises a profound question that transcends astronomy. What kind of object can survive the journey between stars while maintaining structural integrity that surpasses what natural comets can achieve? The study initially began as a comprehensive review of existing observations, but transformed into something far more significant when the team applied thermophysical modeling to the object's behavior during its close solar approach. They tested 3 distinct scenarios to explain what observers had documented since July 2025. The first scenario treated 3I/Atlas as a standard weakly bound comet, the kind composed of volatile ices and dust that typically fragments or outgasses unevenly when heated by the sun. The second scenario modeled it as a fragment from a differentiated exomoon, meaning a moon that is separated into distinct layers through internal heat and gravitational sorting. The third scenario proposed it was lithified planetary crust, material that had undergone compression and crystallization similar to sedimentary processes observed on Earth. The analysis encompassed rotation rates, mass loss calculations, spectroscopic signatures, and structural stability under solar wind pressure. Each scenario was rigorously tested against the observational record, and the results were unambiguous. The weakly bound comet model failed to reconcile with multiple independent data points. Both the differentiated exomoon fragment and the lithified crust scenarios satisfied the observational constraints. The paper concluded that 3I/Atlas exhibits characteristics consistent with high-strength geological material rather than volatile-rich ice. This isn't the kind of hedged conclusion that typically appears in preliminary research. The language is measured yet direct, and the modeling work provides quantitative support for the classification shift. Importantly, the paper does not claim the object is artificial or under intelligent control. It argues that the object's composition and behavior suggest a natural origin, but one involving planetary-scale processes rather than simple accretion in a protoplanetary disk. For months, NASA and the European Space Agency described 3I/Atlas as a comet with unusual features, and their public statements emphasize that comets often display unexpected activity. The new research suggests that framing was inadequate from the beginning, and the agencies may have been operating with incomplete models while independent teams gathered data pointing in a fundamentally different direction. One of the most compelling pieces of evidence comes from the tail structures observed by multiple telescopes since the object's discovery. Independent astronomers captured images showing a primary tail extending nearly 5 million kilometers behind the object, with an anti-tail reaching more than 1.2 million kilometers toward the sun. These dimensions alone wouldn't disqualify the comet model, but the rate at which material left the nucleus created a mathematical problem researchers couldn't ignore. Professor Avi Loeb's team calculated the mass loss required to produce these structures based on the density of particles in the tail, the velocity of the solar wind at approximately 400 kilometers per second, and the brightness of the coma. The calculations indicated that billions of tons of material were released over the course of the object's inbound journey. For a normal comet, this level of outgas would require a nucleus several kilometers in diameter with sufficient volatile reserves to sustain continuous activity throughout its approach to the Sun. However, Hubble Space Telescope observations place strict constraints on the size of the nucleus, and the measurements revealed an object far smaller than what would be needed to produce the observed tail. If 3I/Atlas were a typical comet, it should have either fragmented under thermal stress or shown signs of rapid depletion as its ice reserves vaporized. Neither outcome occurred. The object remained intact. The tail continued to grow. The brightness stayed consistent throughout the entire observation period. This mismatch between expected size and observed activity became one of the critical failures of the comet model. The research team investigated whether localized jets or asymmetric outgassing could explain the discrepancy, but those scenarios introduced new problems related to rotation and surface distribution. A comet with jets powerful enough to produce the observed tail would display spiral patterns or curved distortions as the nucleus rotated. Yet the tail of 3I/Atlas remained straight and geometrically stable. The numbers forced a fundamental reconsideration of the object's composition. The thermophysical model suggested that material with higher density and lower volatility could produce the same visual effect with far less mass loss. Instead of ice sublimating into gas, the models explored whether fine particles were being stripped from a crystalline surface by solar radiation pressure. This mechanism would require substantially less material and explain why the object didn't shrink or fragment during its closest approach to the Sun. Early measurements estimated that 3I/Atlas completes one rotation approximately every 16 hours, a rate falling within the normal range for small solar system bodies. However, the expected consequences of that rotation did not appear in the observational data, and this absence became another critical point where the comet model failed to match reality. When a comet rotates, its jets of gas and dust trace spiral patterns in space, because events on the surface move in and out of sunlight as the nucleus spins. These spiral structures are common in cometary observations and provide a clear signature of rotation. Astronomers use them to calculate the spin rate and orientation of the nucleus, and the distortion in the tail reflects the combined motion of rotation and orbital velocity. 3I/Atlas showed no such spirals. The tail extended in a narrow, straight line for millions of kilometers, and the anti-tail maintained sharp geometry pointing directly toward the Sun. Multiple observatories confirmed this structure across different wavelengths and observation times, ruling out the possibility that it was an artifact of imaging equipment or processing errors. The research team tested whether a slowly rotating comet with highly localized venting could produce a straight tail, but the simulations demonstrated that even minimal rotation would introduce curvature at the scales being observed. The only scenario that preserved the straight geometry required the source of the tail to remain nearly stationary relative to the Sun, which is inconsistent with rotating icy nucleus releasing jets from discrete vents. Another expected consequence of cometary outgassing is spin-up, a gradual increase in rotation rate caused by jet force acting like a small thruster. As gas escapes from the surface, it creates torque that changes the spin over time. Observers often detect this effect through shifts in the brightness curve or changes in the tail structure. 3I/Atlas showed no measurable spin-up during months of observation since its discovery, suggesting that whatever was producing the tail wasn't generating the asymmetric forces typical of cometary jets. The absence of these signatures pointed toward a different mechanism, one that didn't depend on rotation-driven venting from a volatile-rich surface. The research team proposed that particles might be released uniformly from a crystalline structure heated by solar radiation, creating a tail without the rotational artifacts expected from jet-driven outgassing. Comets are inherently messy objects. Their nuclei are composed of ice, rock, and organic compounds mixed in uneven layers. This heterogeneity creates patchy brightness in the coma as different regions heat at different rates. Observers typically see bright spots where fresh ice is exposed, darker areas where dust covers the surface, and irregular fluctuations in the overall glow as the comet rotates and different faces turn toward the Sun. 3I/Atlas displayed none of this variability. The coma maintained smooth, uniform brightness throughout the observation period with no visible hotspots or dark patches. Several teams measured the light curve repeatedly, and the results showed remarkable consistency even as the object moved through changing distances and solar angles. This uniformity suggests that the source of the glow isn't scattered across a rough, irregular surface, but is instead distributed evenly or originates from a central region that heats uniformly. For a comet, this would require an implausibly homogeneous composition with no variations in ice content or dust coverage across the entire nucleus. For a geologically processed object with crystalline structure, uniform heating and particle release become more plausible because the material responds to solar radiation consistently across its surface. The lack of brightness fluctuations also ruled out models where localized vents dominate the activity. If a small number of jets were responsible for the tail, the brightness would spike when those jets face the sun and drop when they rotated away. The steady glow observed in 3I/Atlas indicated that material was leaving the surface continuously and evenly, consistent with radiation pressure acting on fine particles embedded in a rigid matrix rather than gas escaping from volatile pockets. Spectroscopy provided some of the most direct challenges to the comet classification because it revealed what the object was not made of. Those missing signatures forced a fundamental reconsideration of the entire model. When astronomers point spectrographs at comets, they expect to see strong emission lines from water vapor, carbon monoxide, carbon dioxide, and various organic molecules. These volatiles define cometary composition, and their ratios provide clues about where and when the comet formed. 3I/Atlas showed weak or absent signatures for several expected volatiles. Water vapor lines appeared far dimmer than predicted for an object producing such a large tail, and the carbon monoxide to methane ratio didn't match the pattern seen in solar system comets, or in 2I/Borisov, the other confirmed interstellar comet that visited in 2019. The missing volatiles suggested that whatever was producing the tail wasn't primarily ice sublimating into gas. Instead, the spectra revealed hints of metallic absorption features and hydrated mineral signatures that are unusual for comets, but consistent with geologically processed material. The presence of nickel and iron in detectable concentrations suggested that the object had undergone differentiation, a process where heavier elements sink toward the center of a body while lighter materials rise to the surface. This separation requires sustained internal heat, either from radioactive decay or tidal forces, and produces layered structures similar to what we observe in planets and large moons. The nickel-to-iron ratio observed in 3I/Atlas matched the range expected for differentiated bodies rather than primitive comets, and this became a key point in the argument for reclassification. Comets form in the cold outer regions of planetary systems and never experience the heat needed to melt and separate their components. If 3I/Atlas contains differentiated material, it must have originated in an environment where planetary-scale processes occurred. The most likely sources are fragments from disrupted moons or crustal material ejected during collisions. The spectroscopic data didn't provide a complete chemical inventory, and the research team acknowledged that more detailed observations are needed to confirm metallic signatures and measure additional elements. However, the existing data were sufficient to rule out a simple volatile-rich comet and to support the two alternative scenarios proposed in the paper. Differentiated exomoons form when a moon grows large enough to generate internal heat through radioactive decay and tidal forces from its parent planet. The heat melts the interior, allowing denser materials like iron and nickel to sink toward the core, while lighter silicates and ices rise to form a mantle and crust. This process creates a layered structure similar to Earth's interior and occurs in moons around gas giants throughout our solar system. If a collision or tidal disruption shatters a differentiated moon, the fragments carry signatures from different layers. A piece from the outer crust might contain hydrated minerals and crystallized silicates. A chunk from deeper layers could include metallic compounds mixed with rock. The resulting fragment would have high structural strength because the material had been compressed and heated, and it would display chemical signatures unlike anything found in primitive comets. The research team modeled what would happen if such a fragment were ejected from its planetary system and traveled through interstellar space for millions or billions of years. The simulations showed that a dense crystalline fragment could survive the journey, without significant erosion, because its strength would resist the impact of interstellar dust and cosmic radiation. When a fragment entered a new solar system and approached a star, solar heating wouldn't cause the same rapid sublimation seen in comets. Instead, radiation pressure would strip fine particles from the surface, creating a tail without the explosive outgassing that defines cometary behavior. This scenario explained multiple observations simultaneously. The high density accounted for the small size relative to tail production. The lack of volatiles matched the absence of strong water and carbon monoxide lines. The uniform brightness reflected the even heating of a crystalline surface. The straight tail geometry resulted from steady particle release rather than rotation-driven jets. The metallic signatures came from material that had undergone differentiation deep inside a parent body. The exomoon fragment scenario also provided a natural explanation for how interstellar objects form. Planetary systems experience violent events throughout their lifetimes, including planetary migrations, close encounters between giant planets, and collisions that shatter moons and smaller bodies. Material ejected during these events can reach escape velocity and drift into interstellar space, eventually entering other systems as visitors like 3I/Atlas. If differentiated moons are common around gas giants, then fragments from disrupted moons should occasionally appear as interstellar travelers. The second scenario proposed in the paper involves material that underwent sedimentary processes similar to those on Earth, where layers of particles accumulate over time and compress into solid rock through pressure, chemical reactions, and long-duration exposure to heat. On Earth, sedimentary rocks form in environments like ocean floors, riverbeds, and volcanic plains where material settles in layers and gradually lithifies into formations such as sandstone, limestone, and shale. A similar process could occur on planets or large moons with active geology, where material from volcanic eruptions, impacts, or tectonic activity settles and compresses over millions of years. If a collision ejected a fragment of this lithified crust, the resulting piece would have high structural integrity and a crystalline internal structure that resists thermal stress and mechanical impact. It would also carry chemical signatures from the environment where it formed, including hydrated minerals and trace metals incorporated during the lithification process. The research team tested whether this type of material could explain the observations, and the model showed excellent agreement with the data. A lithified crust fragment would have the density needed to produce a large tail from a small nucleus because the particles released would be fine dust stripped from the surface rather than volatile gases. The spectroscopic signatures would reflect the minerals and compounds present in the original crust, which can include the hydrated and metallic features observed in 3I/Atlas. The structural stability would allow the fragment to survive interstellar travel and resist fragmentation during close solar approach. This scenario also explained why 3I/Atlas didn't show the patchy brightness or irregular outgassing typical of comets. A lithified surface heats uniformly because its composition is relatively homogeneous compared to the mixed ice and rock in cometary nuclei. The lack of strong volatile signatures made sense because sedimentary processes remove or transform many of the original volatile compounds, leaving behind crystallized minerals and residual water locked in hydrated structures. The lithified crust scenario requires a planetary system with active geology and long-duration surface processes, which are expected around stars similar to our Sun. Material from such systems could be ejected during planetary migrations, giant impacts, or close encounters with passing stars, and fragments would drift through interstellar space until they encountered another system. The survival rate for these fragments would be higher than for loosely bound comets because their structural strength will resist the erosive effects of cosmic dust and radiation. The distinction between the exomoon fragment hypothesis and the lithified crust scenario depends on detailed chemical analysis that current observations cannot provide with certainty. The research team suggested that observations with the James Webb Space Telescope could discriminate between the two origins by measuring specific mineral ratios, isotopic signatures, and the presence of compounds that form only under particular conditions. For example, certain hydrated minerals form only in the presence of liquid water, which would favor the lithified crust scenario if the geology involved aqueous processes. Metallic compounds in specific oxidation states could indicate differentiation at high temperatures, supporting the exomoon fragment interpretation. Isotopic ratios of elements, such as oxygen and nitrogen, might reveal whether the material formed in the inner or outer regions of its parent planetary system. These measurements wouldn't resolve the mystery completely, but they would narrow the range of possible origins and provide constraints on the environment where 3I/Atlas formed. The goal isn't to force a single conclusion, but to build a model that accounts for all the observational evidence while remaining consistent with known planetary processes. The research team emphasized that both scenarios are natural explanations that don't require any exotic physics or control behavior. They represent what happens when planetary systems evolve over billions of years, experiencing collisions, migrations, and disruptions that scatter material into interstellar space. The unusual aspect isn't that such fragments exist, but that we're now detecting them and recognizing that interstellar visitors might include a wider variety of objects than previously assumed. The failure of the comet model came down to multiple independent lines of evidence that converged on the same conclusion. Comets are volatile-rich objects with low density and weak structural integrity. They fragment easily under thermal stress, show patchy outgassing driven by rotation, and produce spiral tail structures. They contain water, carbon monoxide, and organic compounds in ratios that reflect their formation in cold protoplanetary disks. They brighten unevenly as different surface regions heat up and release gas. 3I/Atlas displayed none of these characteristics. It remained intact during close solar approach. It produced a straight, geometrically stable tail, without spiral distortions. It showed weak volatile signatures and hints of metallic compounds. It maintained uniform brightness without the fluctuations expected from rotating vents. It released billions of tons of material from a nucleus too small to sustain that level of outgassing if it were made of ice. Each of these observations individually might be explained by unusual circumstances or measurement errors, but together they formed a pattern that couldn't be reconciled with the comet classification. The research team tested variations on the comet model, including scenarios with deep insulating layers, asymmetric heating, and localized venting, but none of these adjustments produced results consistent with a full observational record. The paper concluded that 3I/Atlas is inconsistent with cometary nuclei, and that the data strongly favor geological processing as the origin of its composition and structure. This doesn't mean comets can't behave strangely, or that every unusual observation requires a reclassification. It means that in this specific case, the evidence supports an alternative explanation that better fits the observations. If 3I/Atlas is confirmed as a geologically processed fragment, it expands the catalog of what we should expect from interstellar visitors. Until now, the assumption has been that objects entering from deep space would be either comets or asteroids with compositions similar to those found in our solar system. The discovery that fragments from disrupted moons or planetary crusts can survive interstellar travel suggests that we might be sampling material from a wide range of planetary environments. This has profound implications for how we interpret future detections. When observatories spot a new interstellar object, the initial classification will need to consider not just its orbit and brightness, but also its spectroscopic signatures, structural stability, and mass loss behavior. Objects that don't fit the comet or asteroid categories might represent new classes of interstellar debris, each carrying information about the planetary systems where they formed. The research also raises questions about how common these fragments are compared to standard comets. If planetary disruptions regularly eject geologically processed material into interstellar space, then the population of objects drifting between stars could include a significant fraction of fragments rather than just primitive icy bodies. Detecting and characterizing these fragments would provide a way to study planetary processes in other star systems without needing to visit them directly. The question now is whether 3I/Atlas is an outlier or the first confirmed example of a common phenomenon we simply hadn't recognized before. The answer will come from continued observation and from developing better models for how planetary systems evolve and scatter material into space. If the reclassification holds, it marks the beginning of a new category in the catalog of small bodies, one that requires geological history rather than simple accretion to explain. What do you think 3I/Atlas truly is? Is it a fragment from a shattered exomoon, carrying the crystallized signature of tidal heating and gravitational sorting? Or is it a piece of lithified planetary crust, compressed over millions of years in conditions that mirror Earth's own geological processes? The evidence is mounting. The models are converging, and the scientific community is watching closely as this story unfolds. Then, on December 8th, 2025, everything changed. The James Webb Space Telescope completed its scheduled deep infrared observation of 3I/Atlas as the object began its outbound journey past Mars orbit. The data transmission arrived at the Space Telescope Science Institute at 3:47 a.m. Eastern Standard Time, and by 6:15 a.m., the lead analyst had initiated an emergency protocol that hadn't been used since the telescope's commissioning. Dr. Sarah Chun, who had been part of the original research team arguing for reclassification, was awakened by a call from her colleague at Johns Hopkins. His voice was shaking. "Sarah, you need to see this. The Webb data just came through. The isotopic signatures. They're not matching anything we predicted." Within hours, a hastily assembled team of planetary scientists, geochemists, and astrophysicists gathered via secure video conference. The data on their screens told an impossible story. The oxygen isotope ratios were wrong, not slightly off, completely inconsistent with any formation scenario in our solar system or any theoretical model for exoplanetary systems based on current stellar formation theory. The nitrogen, 15 to nitrogen, 14 ratio suggested material had formed in a stellar environment with neutron flux density that shouldn't exist in stable planetary systems. But it was a trace element analysis that made everyone in the virtual room fall silent. Embedded in the crystalline matrix were microscopic inclusions of technetium-99, an element with no stable isotopes and a half-life of only 211,000 years. In nature, technetium exists only as a trace product of uranium fission or in the remnants of recent supernovae. Finding it in a geologically processed object that had supposedly traveled through interstellar space for millions or billions of years was thermodynamically impossible, unless the object was far younger than anyone had assumed. Dr. Marcus Webb, a nuclear geochemist from MIT, ran the calculations 3 times before speaking. If this technetium reading is accurate, this fragment couldn't have been drifting through interstellar space for more than a few 100,000 years, maybe less. The implications hung in the digital space like a thunderclap. As teams around the world began reanalyzing the data with this new constraint, another anomaly surfaced. The hydrated mineral showed an unusual crystallographic structure, one that required formation in the presence of liquid water, but at a temperature and pressure combination that didn't match any known planetary geological process. Dr. Chin pulled up the spectroscopic data again, this time looking at finer details in the absorption bands. There, hidden in what had initially been dismissed as noise, was a pattern. The mineral structure showed microscopic layering at the nanometer scale, too regular to be natural sedimentation, too complex to be simple crystal growth. "This is engineered," she said quietly. "This isn't just processed. This is manufactured." The words felt absurd even as she spoke them, but the data was undeniable. The layering showed periodicity consistent with controlled deposition, similar to what you'd see in advanced materials science laboratories, but at scales and purities that exceeded current human manufacturing capabilities. Within 48 hours, 3 independent laboratories confirmed the findings. The crystalline structure of 3I/Atlas contained evidence of artificial processing at the atomic level. On December 9th at 11:23 p.m. Greenwich Mean Time, the Arecibo successor facility in Puerto Rico, rebuilt after the original telescope's collapse, detected something that had been hidden in the data all along. A graduate student named Marcus Rodriguez was running automated signal processing on archived radio observations of 3I/Atlas from its initial approach. The standard algorithms had found nothing, but he'd modified the search parameters to look for incredibly narrow-band emissions that would normally be filtered out as terrestrial interference. There, embedded in the thermal radio emissions from the object's coma, was a signal. It repeated every 16.3 hours, matching the object rotation period exactly. The frequency was 1,420.4057551 MHz, the hydrogen line frequency, offset by precisely 0.1 Hz. That offset was far too specific to be natural. It was a radio frequency equivalent of a lighthouse beam, and had been broadcasting since the moment 3I/Atlas entered detection range. The signal itself carried no obvious information content, no modulation, no embedded data structure. Just a pure, impossibly narrow carrier wave that shouldn't exist in nature, sweeping across Earth once every rotation. It wasn't a message. It was a beacon. By December 10th, the classified briefing at NASA headquarters included representatives from every major space agency, the National Security Council, and scientific advisors from a dozen nations. The presentation lasted 4 hours and concluded with a single, undeniable synthesis of all the evidence. 3. I/Atlas was not a natural object. It was manufactured. It was young, possibly only thousands or hundreds of thousands of years old, not billions. It had been launched or ejected from a planetary system with deliberate engineering of its material composition, and it was actively broadcasting a beacon designed to be noticed by any civilization capable of radio astronomy. The geometric stability of the tail wasn't the result of unusual geology. It was a result of precisely controlled particle release, likely from embedded mechanisms that still function after an interstellar journey. The lack of rotation-induced spirals was an anomaly. It was evidence of attitude control. The uniform brightness wasn't a coincidence. It was deliberate thermal management. Dr. Chen stood before the assembled officials and delivered a conclusion that would change everything. 3I/Atlas isn't a natural fragment traveling through space by chance. It's a probe. Someone built this object, launched it into interstellar space, and designed it to announce its presence to anyone who looked closely enough. The question isn't what it is anymore. The question is, who sent it? Where are they? And what do they want us to find? The room erupted into urgent conversation, but Chen wasn't finished. She brought up one final image on the main screen, a trajectory analysis that traced 3I/Atlas's path backward through space using gravitational perturbations and velocity vectors. We trace its origin point, based on its current trajectory and velocity, accounting for gravitational interactions with nearby stars over the past 300,000 years. 3I/Atlas originated from a region of space approximately 180 light-years away, in the direction of the constellation Cygnus. There are 17 candidate star systems in that volume. 12 of them are confirmed to have exoplanetary systems. 3 of them have planets in the habitable zone. She paused, letting the implication sink in. And the beacon is still broadcasting. Every 16.3 hours, it sweeps past Earth, a perfect hydrogen line signal offset by exactly 0.1 hertz. It's not trying to communicate. It's telling us where to look. The room fell silent as the National Security Advisor stood. What are you proposing, Dr. Chen? I'm not proposing anything yet, she replied. But I am saying this. 3I/Atlas is the most sophisticated artifact ever discovered, and it came from a civilization that achieved interstellar travel at least 300,000 years ago, possibly much longer. It survived a journey that should have destroyed any natural object, and it's still functioning. She looked around the room at the faces of the most powerful scientific and political figures on the planet. They sent it for a reason, and I think we need to be ready for the possibility that they sent it here specifically, that this wasn't a random trajectory. Someone out there built a probe designed to be discovered, designed to be studied, and designed to point us back toward its origin. The question we need to answer is, are we ready to look? As dawn broke over Washington, D.C. on December 11th, 2025, the world remained unaware of what had been discovered. But in laboratories, observatories, and government facilities across the globe, preparations had already begun. The largest radio telescope array in history was being retasked to focus on the 17 candidate stars identified in Cygnus. The James Webb Space Telescope's entire schedule was being quietly reorganized to conduct deep spectroscopic surveys of the exoplanets in those systems. 3 nations with deep space capabilities began preliminary designs for a fast-response probe mission that could reach 3I/Atlas before it exited the solar system in 2027. And in a secure facility beneath the Kennedy Space Center, linguists, anthropologists, mathematicians, and physicists were assembling the framework for humanity's response. Not a message sent blindly into the void, but a reply to an invitation that had traveled across the light years. Dr. Chen stood at the window of her hotel room, watching the sun rise over the Capitol. Her phone buzzed with an encrypted message from the director of the SETI Institute. The listening array is online. 17 targets locked. Whatever happens next, we'll be ready. She thought about the crystalline fragment racing away from the sun, its beacon sweeping steadily across Earth with metronomic precision. Somewhere out there, 180 light-years away, was a civilization that had built it. They had achieved what humanity was only beginning to dream of, travel between the stars. And they had left a trail of breadcrumbs for anyone willing to follow. The story of 3I/Atlas wasn't ending. It was just beginning. What happens next would depend on choices humanity hasn't yet faced. The universe just sent us a message written in engineered stone and radio waves. The only question remaining is, what will we say back? Share your thoughts on this extraordinary revelation. The conversation about humanity's place in the cosmos has just fundamentally changed, and we're all part of what comes next.